next session is already there. Sir has already joined our one of the another outstanding researcher. That is, he is working also some of MEMS and basically optical sensors and MEMS, and he is working, and he's an outstanding researcher. Not only researcher, he was a very good academician from Tezpur University. Professor Parthopratim Sahu is the now head of the department, also professor and head. So it's a well-known person. Recently, he has got different, even if he has got 2% of Stanford University researcher, he has received this award also. So he's one of the not only academician, researchers, even if administrator also. He is an outstanding so he's already with us, and already because 2:15 is the time for next session. And he has joined minimum 30 minutes before. He is very active and very sincere for this purpose also. So
don't tell this.
So that way. So otherwise, if you have
thank you,
thank you, sir. Thank you. Good afternoon, sir. Namaskar, sir.
Namaskar.
How are you, sir?
I was busy with some work.
Yeah.
Then he Professor Indratri, Maity, request me to join.
Yeah.
Okay. Half an hour before I join it.
Yes.
Your lecture is good. We are working on MEMS design.
Thank you. Thank you, sir. Thank you very much.
We are very,
so if you have no question, we can go for the next session. The Professor Parthopratim Sahu, that I have already given the introduction. He was
now should I wait a little bit or we will start immediately?
We can start, no problem, sir. Everything was there, near about 100 people was there. Now there is only 86, 90 has come already. So okay. I think they will another 3 people. Will
so we have to share this thing, no?
Yes.
Just I'll share it, okay?
Okay.
Now I'm sharing. It was it was Share. Hello, it is coming or not? Please.
Yes, yes.
Yeah, it is coming.
Yes, it is coming. Yes, it's coming.
It's coming. So full screen, no? I have to give full screen.
Yes, it will be better.
No, it will like that. I have to shift some of the slides now because I have to shuffle the slides. When I presenting, I'll shuffle the slides.
So, sir, you can increase the view, that some percentage you can increase the view. Then that will be better for better view, sir. In above one is view.
Okay.
That next right side, next, sir.
Full screen.
View.
We will increase the view. No, click. I want to click. No, it.
So it is coming. Okay. So thank you, Rao sir, that your nice presentation, and it is my great privilege to be here to give you also thanks to hear that our FDP has now it is in 3rd day, and there are few people are left. I think.
Okay, I'm making it full screen. It will be better, huh?
Okay. So every talk is very good in our case, and also in Rao sir pressure sensor, you know that it is a very also a very hot topics nowadays. So he has given nicely and wonderful, outstanding idea they have given also, and sir has given also different aspects of the pressure sensor. Sir, once again, thank you very much, sir.
Thank you, sir. Thank you, Maity ji.
Accepting my request, actually.
It's a great pleasure for me to participate in your event, sir.
Thank you, sir. And next speaker, already I have told that Professor Parthobotim Sao, and he has completed his master degree from IIT Kharagpur, then IIT Delhi, then PhD from Jadavpur University, and he is basically working in the optical sensors and different sensors, and also he is working a MEMS lab, MEMS sensor. He is a very renowned professor that I have told that he has got the recently award the Stanford University 2% scientist and researchers. So he has lots of awards. He has worked in many places like NIT.
Hello.
Yes. I'm just giving introduction. So
Okay.
he has worked many places like NIT Jalandhar, Nerist, then Tezpur University. Now he is the professor and head of the Department of Electronics and Communication Engineering, Tezpur University. And whatever already previously I have told is you can see that if you will search these research activities in the internet like ResearchGate or like Google Scholar or Scopus, you can find out that what he is working is a very good researcher and lots of awards. He has filed already approved the patent also. So, sir, over to you.
Okay,
Now
thank you.
Start your talk.
Thank you, Niladri. Nice presentation. Nice introduction to me. I'm not like that also because I normally do not like to have it should not give a lot of introduction to me. Anyway, topic is biosensing application. Just before that, I'll like to show some of the slides for our work in our group, our activities in our group. Our main area is optical networks component. From the starting honor, from MTech honors, I'm working on that. And in fact, we have developed the Indian network and we have designed it and with protection system and within routing. In hardware also, we have some of the contributions we have in terms of switch, in terms of WDM. We have fabricated some of the hardware in our laboratory. So next topic of my research is spread spectrum technology in wireless communication. In fact, we have done some work on ISRO. We have fabricated the prototype system. We have developed the prototype system. Probably they will be used in the satellite multi-channel system we have developed. And next, we have worked on neuroengineering. Neuroengineering, we have modeled the nerve, injured nerve, abnormal nerve with different diseases, minute diseases. And some of the slide I can show you where you can have some of the electrode used in the electrode sensor used for the measurement of nerve signal, which can analyze the conduction velocity of the nerve. Hello, I'm meeting. Hello.
Yes, sir.
So we are working on MEMS devices. We have designed some fabrication system. Fabrication setup is there. We have fabricated some of the MEMS cantilever sensor. We have had in last lecture. They have designed it, and RF sensor. We have RF circuit. They have designed it. We have fabricated in our laboratory with collaboration with the, because Jadavpur University, some of the NIT, they ask for fabrication. They have designed it. We have fabricated in our laboratory. RF sensor, cantilever sensor, some of the micro sensor we have developed for other NIT. So why I'm showing all this? Because if anybody interested to collaborate with us, to do work with us, then they are welcome for on these fields. Apart from that, some of the devices already recently we have started working on global warming for fabrication of alternative energy source like water spreading, solar cell. In our lab, this activity is going on. Okay, it's an Assam facility where we have to do everything. Whatever cutting edge technology will be there, so we have to do everything since it is an Assam facility. So, coming back to our actual lecture, that biosensing. Before that, I just tell you what are the topics I cover in this lecture. So we'll discuss mostly we discuss about the e-sensor. We'll not discuss the chemical sensor or other sensor. E-sensor, mostly we discuss sensor, e-sensor. In some of the slide I can show you the optical sensor. Already we have started working on that. And then next topic I'll discuss why we need e-sensing. Then some of the biological smelling, testing, modeling, how we can use in the e-sensor, basic idea, basic principle, how we can use it for biological samples, biological e-sensing. And different e-sensing techniques I'll discuss a little bit, ENOS, ETA, EI. Then some of the application we have targeted food quality detection, even clinical studies, case studies we'll discuss here. Some of the limitation, errors, advantages I discuss in the lectures in this lecture. Okay, then we'll discuss about the conclusion. So, what is the e-sensing? Sorry, e-sensing. Basically, it converts the physical signal into electrical signal for measurement, for analysis, and display control. It's very too easy to display in the electrical. That is why we need to convert any physical signals to electrical signal. So that is the purpose of sensor. Actually, especially there is a difference between sensor and transducer. Transducer should convert energy to other energy, one type of energy to other energy. Yes, different is that we will try to discuss about the physical parameters, like as I told you, physical parameters, the smell, taste, touch, hearing. These are the physical signal which coming from the physical element. It's coming from the physical element. So in transistor, it's just convert. It also converting, but transistor just convert any type of energy to other energy. So this is the difference. So what is the physical? As I told my topic is lecture now is sensing. So we'll consider the sensing only, sensing part. So some of the applications I just tell you for your reference. Industrial, here for industry, you try to measure temperature, moisture content, flow control, level control, pressure, motion, access. These parameter industrial parameter will do it for industrial applications, in industrial application. Environmental, you try to see what is the smoke in the environment, find out the smoke, carbon dioxide content, carbon monoxide, dangerous gases like H2S, many other gases, dangerous gases, there. How much concentration is there in the environment, which are harmful to the human body or other animals, other biological elements, biological animals. So flammable gases, explosive gases, alcohol vapors. So these are hazardous gases which has to be measured, has to be monitored in the environment. That is why sensor is used. In case of food quality detection, you try to measure the flavor, color, and how much spoilage is there. It's not mentioned, spoilage is there. You try to. In fact, we have done some work in food quality detection, meat spoilage, fish spoilage we have determined in our laboratory. I'll show you later in my lecture. Okay. And biosensor basically you detect the protein. Some of the protein already we have started working on detection of protein, and diabetics monitoring through glucose sensor. And already we have done some work with my PhD student. And cardiac diagnostics also you can do. I have not discussed this cardiac diagnostics. You can use the electrode for and fat content, pH sensor, nerve condition testing, as I told in the first slide, that nerve condition, how to measure your nerve condition by measuring the NCP, nerve conduction intensity, and the action potential. This is called CAP, complex action potential. CAP signals, by analysis of CAP signal, we can see the nerve, what is the condition of the nerve, whether channel blocking is there, or whether NCP is decreasing, nerve conduction is decreasing. Because it leads to the different nerve disease like Alzheimer's, Parkinson, GBS, different disease may be analyzed through this by seeing the measure. So I'll show you 2-3 slides for that. Okay. So why you go for e-sensing? First is the repeatability. You want, because sensor should reproduce the things, reproduce the same signal again, and repeatability. And time also should be very fast detection, so that we can monitor on-site measurement or rapid measurement, or maybe online measurement. It can be possible using that. Okay, some of the technique I'll discuss a little bit if I get time. Lack of facility of sensory analysis. This is another problem we're getting, and it should be non-destructive. So most of the sensor basically non-destructive. You can reuse the sample again. Okay, so some of the common sensor using sensor is metal oxide sensor, MUS sensor, metal electrode is used, optical waveguide sensor is there. We'll discuss some of the sensor. We'll discuss. And metal oxide sensor, we can use two approaches. We can use resistive sensor and a capacitive sensor. Some of the capacitors we have developed in our laboratory. I'll discuss how we can mathematically model it, how we can experiment with it. Because I never use the software for other company or other make, which I normally use. Started from the mathematical modeling foundation, then we design using our mathematical formula. We design ourselves. Okay, this approach I use in our laboratory. Most of the work we do not use, because if we use a software, probably is there accuracy. Okay, we have designed it. We may not be good for the sensing. Okay, so that is the approach should be like that. For me, I'm telling you what approach you should adapt for design and fabrication. You should have your own mathematical modeling develop and design it. And if you do that, then we can make structure, we can modify structure, we can make your own structure. Some of the structure I'll show you how we have done it. Hello. So e-sensing, why e-sensor? Why we require e-sensor? Some of the already I have told, reversibility is there, response time is very low, selectivity is very high, sensitivity is very high, and energy consumption is low, and fabrication cost is very low, and it is portable. We can use in on-site measure. In different sites, we can measure the things. We can take it to other places. So biological, some of the sensor, sensor, how it works. The signals pick up from the thing. There's a chemical sensors in the thing. How biology, the human knows how it's sensing, or knows of any animal, how it is sensing. I'm just telling you. It takes the signal, and there the sensor, the knows it says converting the electrical signal going to the motor nerve, or it can directly go to the head, the nerve, the head, and there we're seeing the calibrator signal is there, and they compare it like that. They compare it and they give the decision. Whether it is hydrogen gas, oxygen or nitrogen gas, a good smell or bad smell, all this they can give the results. This is the way we can do it. But something gases we cannot sense by using biological, because this database is not there in your human, in that head, I mean motor nerve or head, it is not there. So that is why we cannot take the decision. Brain, it is, in fact, it is called as brain. And some of the smelling, you can see the structure. The mucus is the olfactory epithelium. There is a chemical which can pick up the gases. There is a chemical changes, structural change in the chemical when it interacts with that. And after that, the chemical changes will be picked up by the nerve. It converts to nerve. It's very difficult to tell now because it is not known how it is converting. It's converting the electrical signals because sodium potassium ion may be there. Due to sodium potassium, the chemical, the sodium potassium ions movement and sodium potassium also will be changing. Because of that, the current produced, very soon current will be produced, and it goes to the human brain, and they take the decision. Database will be there, they take the decision. So one question comes to my mind: how database is made? When child born, then automatic database will be made in a human body. This suppose the sweet test or short test or bitter test. This database is already in your body. When child born, they take the body and automatically it has been trained in the brain itself. Okay. Same concept will be used in e-nose or e-sensing. Okay. Now, suppose you take the smell, then after that different sensations it will be coming. How it is, this is a human sensing, it is a instrument sensing, e-sensing. So smell will come, different sensor will pick up the things, then process it, and data will be going, and it will be calibration with known sample, and this calibrated data will be there, and it's compared with that and take the decision. Just like a human body, electronic, the sensor, this is a olfactory sensor, then this, through that, it will convert it to electricity, because there are a lot of ions actually, sodium, potassium, it changes. When chemical changes will be there, when these gases will be coming, directly interact with the chemical which are there in the cells, and after that sodium potassium balancing, sodium potassium that ions also will be changing, concentration of sodium potassium or movement will be changing. So through that olfactory bulb, through that we can change the electrical to go directly to the brain and take the decision. So now, as I already told, so it is very fast, simple, real time, and sensitive to very low concentration. Okay, because human body, sometimes your database may forget the may or may not interact properly. Interpretation may not good, but e-nose, if you convert e-nose or e-sensor, then chance of getting error will be very, very less. We get perfectly, you can detect it. Because it's machine. Whatever will be teach to a machine, or we learn the machine on the basis of learning a database, it will automatically take the decision. So some of the e-sensing, I'll just tell you, sensor. This is the gases will come. Sorry, gas will come. So that is the molecule which interact the order molecule. Order molecule, suppose oxygen content is there. Okay, so it will interact with that, and it, at 400 degrees centigrade, and we can get the changes, and these changes will change it because electron ion also be released from this, and these electron ions will be charging the sodium potassium ions, and that is get the change of current, and this change of current will go to the human, and that will be processed in the brain, and it will give the decision. Okay. Okay. Some of the volatile compounds which influences the flavor were hydroxyl groups, aldehyde, ketones, acids, esters, sulfurs compounds. Sulfur compound means H2S, you can say dimethyl sulfide. Nitrogen content gases, which is used mainly in the food quality detection. I'll show you some of the slides. Nitrogen basically a main component of the protein. So they are also, we have to interact the nitrogen, and you can get the result. So for detection of protein in the blood, we have done some of the work in our laboratory. If I get time, I'll show you. Oxygen, we can use it as a oxygen content molecule, oxygen radicals, we can use it. Some of the common sensor is used. I'll just tell you, metal oxide semiconductor. It is basically stable, long lifetime. You can reuse the sensor and short response time. But only drawbacks is the low sensitivity, slightly low sensitivity in compared to others, and little bit high energy consumption, because metal oxide is a non-conducting, and that is why maybe high energy is required for that. And we have to see that what type of sensor will be used in what condition. That depends upon the what type of material we are sensing, and what is the place you are sensing. Suppose you want to sense the quality of aviation fuel. Aviation means aircraft fuel. While running the aircraft, we have to the pilot has to monitor the water content of the fuel. So there, if you use the, if you transmit the electricals through that, it's a flammable. That is there will be fire. And a huge accident, maybe huge accident will be there in the plane. So that is there. You cannot use this type. So we have to see the site where you can use it. There we can use the optical sensor, where only light can pass through that. If electrical signal will pass through, current passes through the aviation fuel, problem will be that there may be a fire. Okay, there may be distance takes place, little bit distance takes place. It is highly flammable. It will got fire, and explosion may be there. So that is so we have to see the place and what materials we are measuring. So according to, we have to choose the sensor. That is the first thing we have to do. Okay, before going to design, we have to specify. We are going to design, specify the place and what material we are going to sense it. These two things we have to get the thing from the customer. They not design, fabricate everything. Okay, so this is very, very important thing. So some of the gases were tested in our laboratory, not by me, by other faculty in the department. In test nursery, ethanol gases we have used for ethanol sensing ethanol process. We have used titanium dioxide detection TMA, and zinc oxide also we have used for TMA detection. And so we'll discuss a little bit of different types of gas sensor. Main thing is that, as I told you, how do we have seen main drawback of the metal oxide sensor. I told that sensitivity, very low sensitivity. So in our lab, we have mathematical model, one type of structure, the spot sensor structure, and to increase the sensitivity. We are successful to increase sensitivity. I just tell you why we use this type of structure. So this is a spot structure. Spot structure. We can see the metal spot, metal contact is a parallel capacitor, and backside we are making the whole area we have covered with the metal contact, and top side sensing area we make it small spot, metallic spot, and from there we make the contact. Okay, why we do that? We want to try to increase the sensing area. If we increase the sensing area, automatically your this poria automatically your sensitivity will be increased. So that is the purpose why we have this spot type sensor. If we increase the sensitivity, this area automatically sensitivity increase as well as response time also increase. It is so we have designed the things using the this spot structure, and we have designed it, and we have made it for that, and we have made the sensor. And the details I'll come to later little bit. Little bit details when I discuss the food quality checks. I'll discuss there. I'll tell you again. E-tongue sensor. So e-tongue sensor we have seen in your tongue, there are different portion we can sense it. All the portion we cannot sense the same taste, like sour or salt, sweet, bitter. So they are different portions. As I told you, you can see in the display that different type of area we can use it for sensing. Bitterness is a little bit here, and other portion you can see how we can. This is the actual tongue, how it is sensing. So when chemical, particular chemical, I told you what type of chemical representing the bitter, what type of chemical representing the sour, what type of chemical representing the salt and sweet. Okay, so after that I'll discuss how it is doing. Just 1 minute. Okay, bitter is it contains nitrogen atoms, which represent the bitterness. We have to, if you want to sense the bitterness, then it should have nitrogen atoms. Nitrogen molecules should be sensed by your chemical. Okay, so then only you can sense them. So quinine, batrax, these are the bitter chemical, as for example. Then sour. Sour, how it is sour? It is a hydroxyl group which represents the sour, and their COH group will be there, and chlorine content hydrogen group is there, HCl. They are also sour, acidic, basically acidic type of things. These are representing the sour. Organic chemical which depends on is COOH. COOH. You see the structure. COOH. Acetic acid, vinegar is there, tartaric acid is there, even lemon also some ascorbic acid or something like that is there. So this every year we should have a COH group. COH group show the sour. Okay. Salty group means metal and chlorine group will show the salty. Chlorine group means chlorine, bromine, iodine. They are repeating sour. Okay. Sweetness basically it is a carbonyl group, ketone group, aldehyde groups. Some of the aldehyde glucose, the aldehyde groups I have shown in glucose, sucrose is there, and the carboxyl group is there. So they represent the sweetness. Okay. So these are the structure we have to know. These are chemicals which are normally used. So according to the radicals group, radical groups in the chemical, we have to represent the sensing materials. Very important. If you want to make e-tongue, you have to know that what should the sensing material. This material should be interact with the hydroxyl group, which should be interact with the chemical. Then only we can detect the sweet, or you can detect the sour. I have shown sour, what type of radicals depend on sour. So we have to know of this chemical. So accordingly, you have to represent the chemical sensing materials. Once you choose the sensing materials, I just show you some sensing materials. Sorry. I'll come back. Okay, I'll come back again. So before that, I'll discuss this, then I'll come back that one. How we'll design it. Design part I am not shown in the structure design. Design structure I am not shown. In fact, this e-tanks recently we have started working with CDEC Kolkata, Professor Dr. Ramanan Bhattacharya, director, and they asked me to fabricate the e-tank sensor. Already we have started fabricating. We have one sample here. So we have used the 4 electrode. One is reference electrode, 5 electrode, which that electrode is made up of such a chemical that it repels the salty, it repels the sweet, sour, and bitter. Okay. So 4 electrodes we have made for them with different conductivity or different materials we use for different band gap or different work function. So we have designed in the laboratory and we have fabricated for them. They are going for testing. Recently, we have seen this. Now, just coming back to the, I not show all the slides. Some of the slides, important slides, show you. Okay. This is EMG signal from the brain. How electrode, there are special type of electrode is used. Electrodiography, ECG signal, special type of electrode. It pick up the signal, ECG signal from the body. Okay. EMG signal also take the from body, the electrode, which is basically not testing the muscle and conductor. ECG basically heart, condition of heart we can detect it there. Detect it. Okay. And some of the microelectrodes we have designed it here in the laboratory. We could not, some of the fabricated, but we not get the, we have not got, we have due to limited facility, we cannot make it accurate. That is, we have stopped now. Once you get the instrument, because you require to make a electrode structure, a microelectrode structure in 10 micron, 20 micron. So we don't have facility for deep reactive analysis. So that is, we could not make it properly. But we have developed, but it's not giving it. So we have stopped doing that. I'll show you how we have done it, how we have designed it. Okay. NC measurement, I'll show you. So as you have seen, So human nerve, to see the human nerve, not only one action is there, human nerve having this bundle of action is there. Okay. So that means the large number of nerve join, make it bundle of nerve fiber join together, make it single nerve. The nerve fiber is there. These are, so we have taken the, we have this type of model we have taken. So we have taken one nerve, the circular in nature. So in circular in nature. So make a surrounding nerve, effect of surrounding nerve. Okay. If you want to analyze the part of this nerve, so you have to take the effect of that, because there is a coupling of the signal, because they are close together, placed together, so there is a coupling. So you have taken only surrounding only. So on the base of this model, we have mathematically derived the formula. This is the formula we have the conduction velocity in terms of sodium, potassium. As I told you, sodium, potassium ion also very important here. So if you have to know the concept of sodium, potassium. So when signal is coming, suppose your smell coming to your nose. So this sodium, potassium ion voltage and this would be changing. So because of that, the signal will be generated, velocity is changing, signal will be generated, and amplitude also will be changing. Okay. So this formula, with this formula, we can analyze this thing. So we have done it. So we have used a frog. So we try to, in our experiment in the laboratory, we try to see the how can model, how can measure the demand. We have seen we have seen, just I'll show you. This is your nerve. Okay. Nerve conduction is a different type of conduction. This is not a normal conduction. So here there is a myelin thickness. This instituted layer, myelin thickness, is very much effective to increase the speed of the signal. Okay. If this myelin thickness is reduced, then signal will be slow. Okay. Here it is coming the node of Ranvier. So here signal is jumped. Signal will jump electrically, electromagnetically, go to directly, and due to that it will increase speed increase. Okay. If myelin is reduced, then jumping will not be there. So the speed will be reduced. Okay. So if you want to analyze the nerve condition, we have to see that how much thickness is there. Okay. This thickness of myelin will be changing. In most of the nerve disease, it is demyelinated. It's called demyelinated. Myelin thickness is reducing. Okay. Most of the nerve, it may be the Alzheimer or maybe Parkinson. It may be the nerve in the brain, the nerve, motor nerve. So this main problem is this myelin thing is reducing. Due to that, nerve conduction is reduced, or some of the channel will be blocked, sodium potassium will be blocked. So if you can analyze, then you can analyze the nerve condition. Okay. Now we come to the why we have taken frog. There are two reasons we have frog we have taken, okay, to verify our model. One is first is that frog nerve is very similar to the human nerve. It is also having bundle of nerve. If you see the nerve, it's same type of nerve. We have shown some of the figure. If it is there, I'll show you. We have taken the cross of the nerve. We have taken the nerve signals. So here we have a nerve chamber in our laboratory. We take out the nerve and see the first we have taken normal frog, and we have get the result. Now question comes: how we can demyelate the frog? How we can demyelate the frog? Now the myelin thickness we have to reduce. How we can do it? We have seen in the village, from rural area, from village area, I have seen when a snake bites a poisonous snake bites the frog, we have seen that frog will be senseless. Then from there I thought that maybe myelin thing is reducing, maybe some effect is there in the nerve. So also from that concept, we try to use the same experiment in the frog. What we have done it, we have taken the frog, take out the sciatic nerve, then we teeth into the snake venom with different concepts. Snake venom is available in our university. From university we have taken and we dip it. We have tried to see how much myelin thickness is there. Okay, we try to analyze the signal. So we have found that mainly two chemicals, PLA2, it reduced the myelin, because PLA is in PLA is a one type of chemical. It is inside the snake venom, snake poison. So there, this should be dissolve the myelin. That is the myelin reduced. Myelin thing is reduced, and because of that, it will be senseless. And second point we have got that there is another protein is there in the snake venom that is called three-finger toxin. This three-finger toxin, what do you do? It will bonded to the sodium potassium ions, and because of that, the action potential is going down. Because of that, signals not going to the destination. Suppose we pick up the signal from the leg, going to the brain to analysis, it cannot pick up the signal. Okay, I hope that this same type of effect is there when snake bites the human body, because it demyelinated and as well as the channel block is there. That we have done. That is we have done. This paper is been published in the Nature Scientific Report, and with the help of this activity we have done with the molecular biology biotechnology department. And because do not know about the biology. And same experiment we are doing with the Defense Research Laboratory for neuropathy, diabetic neuropathy. Diabetic patient, how it degrades the nerve conduction, So that try to take, listen, you are doing that. Now, this is the, as I told you, we have taken the myelin thickness. This is the myelin thickness, you can see it, myelin thickness is there. And we have taken the cross section, we have seen that in single nerve, there are lot of nerve, bundle of nerve is there. If you take the, in the middle one nerve, there is 6 nerves surrounding. So that analysis we have done mathematically, and we have designed the thing, electrode, and we have analyzed the signals. And we have determined the how much myelin thickness is there. Mathematical equation. We have used the transmission line model. Okay. Why it is related to the electron? Because we have to use the transmission line model for analysis. Okay. There's communication, the transmission line model in the microwave we have studied. So that same model, mathematical model, we have used it here. Okay. This is for the, as I told her, we have done microelectrode for measurement of cell size or measurement of cell, how much cell voltage is there. So we have used the circuit, and it's a equivalent circuit. Okay, and this is the actual model we have done, mathematical model with cell membrane. So these electrode, these are electrode which is connected with the cell membrane, is penetrating, and we have pick up the voltage, cell voltage, and measure it. Okay, this design we have done it and fabricated also in the laboratory. But the electrode height is very low, so that is you could not measure properly. So at present we have stopped this one. So if I get time, we can do it later on also. So coming back to optical waveguide sensor, this is one of the field we are working here. Since my background is optical, so we try to make some optical waveguide sensor and we analyze it. So why we go for that? High speed, high sensitivity, non-destructivity, and high accuracy. Another advantage is that it can detect without sending the current, electrical current. Okay. Pressure is the flammable. Suppose you want to analyze the flammable chemical, how much purity is there. Petrol, we have done for petrol, we have patented. We have done for the aviation fuel. We have petrol aviation fuel, and we have done for transformer oil also. Transformer also we have to check the insulation. Okay, if insulation is spoiled, then that will blast in the transformer. So that is, we have to check the insulation. So that type of analysis we have done it by optical waveguide sensor. I just keep it. Mathematically, we have modeled it. You know the principle of the waveguide sensor is very well known. Total internet reflection is used. This is the angle, critical angle, and mathematically we have represent. Okay. Now we will go further. The optical waveguide sensor, how it is in the bio signal sensing, chemical sensing, and clinical diagnosis and order tracing. These 3 portions will be topic I'll discuss here. Okay. So design part I have told, I will go into that. Just let me see. Yeah. I just keep it. But these are the things. Detailed analysis there. I will not go it. Because I have to cover other sensor also. Theoretical modeling. We have taken this model. Okay, planar structure we have taken. Sensory area, we have increased the area. We have taken out the cladding. So here what we do, remove the cladding. This top surface we remove the cladding. This cladding, we have housed it in the cylindrical plastic structure, and chemical enter inside this cylinder, and this chemical will be used as a sensing material. This technique has been used here. Mathematically, I have modeled it. We have used the waveguide equation, mathematical model, and mathematical model. Then we fabricated. It is not fabricated in our lab. We have fabricated in ISC Bangalore. This we have fabricated. This is setup we use for calibration, power measurement. Okay. I'll show you the glucose concentration measurement. I'll show you how we have done it. The design part. Now come to the additional part. As I told, so what happens is petrol its cost is more. What people do, many people used to do the malpractice. They are doing. They are mix the petrol with kerosene diesel so that they can get more profit. They can get the more profit. Okay, so they mix it. Interested, they mix it and get the things. Okay, so if you do it, your car will be spoiled. Maybe environmental effects because of this spoilage chemical going out. Your condition of the automobile or car or bike will be bad, and as well as that it will a lot of effect in the environment because extra carbon dioxide means there will be warming, extra different type of gases is coming out, hazardous gas coming out, then a lot of problem in the environment. So what they use it, what we have used it, just tell you. So we have mixed the things, then whatever design sensor we have fabricated, and this sensor we have pushed the petrol diesel, mixing petrol diesel with known sensor, and see the effect of refractive. Because if you mix it, refractivity changes. Refractivity changes means your cladding refractivity is also changing. Then the conduction optical through the waveguide also will be changing. So by measuring the intensity of signals, we can detect it, we can calibrate and we can detect it. So this is the thing we have used it. This principle we have used it in our sensing. Yes, sure. Okay. We have made for this sensing, and what we have done, we have managed this by calibration. We have arranged it. This is sensing. We have seen the light, and through syringe pump, inject the petrol kerosene, and we calibrate it with that. By through power detector, we can measure the power of the signals. Okay, the technique we use it using helium laser. So if we use the helium laser, it's costlier, and we have to use it. So how to make it portable? Next step I'll tell you. I'll show you another thing. Okay, this is called glucose sensor. Before that, I tell you the glucose sensor, then I'll discuss about that. So here we have seen that measuring before that Professor Srinivas has told that about the glucose measurement. Most of the sensors used in the glucose measurement, we cannot make an online measurement of glucose. Okay, it is not rapid, and sample volume required for that is very high. So for that, what we have done it, we have want to try to measure the online. So what we have done, we have used the lab on chip. Okay, lab on chip purchased from the market. Okay, from Germany we have purchased. It just demonstrate because lab on chip can fabricate in our laboratory also. It's not a difficult thing. We have not fabricated. We have taken from the lab because they are already calibrated things. So we have taken that there. Here, one input we have put the blood, another output from the output of the lab on chip. Left side is a lab on chip. From there we have taken the signals and for measurement, and coming to the sensor, optical sensor. I'll show you that figure. This is figure you can see. Okay, so signal is pushing the signal in one of the input here. Okay, one of the input here, and signal take up from the this. So this pipeline we have designed in our laboratory, and side also we have designed considering the fluid flow technique. Okay, fluid flow equation. So this is the fluid flow equation we have taken, and we have analyzed, we have designed it, and we have got the 5 centimeter length we have got. 50 centimeter length we have got for measurement. Just I'll show you the things. Okay, this is a setup we have made it for calibration. We have used a helium laser, but in fact, helium laser is very costly. It is not portable. We have used a laser diode. Later on, I'll show you how we have used the laser diode. Okay, so here we have seen this from the pipeline. Blood will push in the one of the output. Okay, it can come out of the human body also. Okay, and it automatically separated. The lab plasma will go to the sensor. This is a sensor we have measuring, and we have calibrated things. Hello. So we have measured it and we have calibrated things. The setup we use it, and initially we have not taken the blood of the human body. We have taken the rat. So rat we have made it diabetic by injecting that with streptomycin. Okay, it is giving the diabetic 1. The diabetic 2 also can make it. We have not made it, but we have made the diabetic 1 by injecting streptomycin. If you want to get a diabetic 2 of rat, we have to use the fat. We have to feed the fat to the rat and make it. It will be diabetic. So we have used that animal model with the help of DRL, Defense Research Laboratory in Tezpur, and we have made the sensor. We have taken the samples. We measure it. Okay, with glucose concentration from the rat and using your signal measure from the signal, normalize it without samples, means air media, we get more signal. Once you push the samples, we'll get the signal. The signal measure in the detector, it will be low. So we have analyzed it and we have made the curve. This is a calibration curve. From there, we can measure it. So unknown sample, we have used it. This is a calibration curve. Number of the glucose with respect to number of days. Okay, how glucose is changing with the number of days after injecting the streptomycin in the rat. We have used the not streptomycin, the Ultrasonography. Streptomycin can do it, but we have used Ultrasonography here. Recently, we are doing with streptomycin. Okay. The glucose measurement, what is the flow chart we have used here? So we use from the rat, blood sample is taken. Then it is go to the lab on chip. It is separate the blood into the blood plasma. Going to the through the fluidinator. Fluidinator, that's what I have designed. This is not designed. The fluidinator we have designed, and along with the optical waveguide sensor. After getting the signals through microcontroller, we can measure it. So this is the technique we have used. So previous section we have seen, just 2-3 slides before, we have seen that we have used the helium laser. We are not using helium laser now. We are using the laser, simple laser to make it very cheap. We have purchased, hardly it is 20 rupees, 30 rupees. We have purchased from the market and we have made it to make it very cheap. This is the things we have developed. Lab on chip, Sensor is there. Sensor is there. Sensor is very low cost sensor. Okay. This display is there. Signals are coming from the human body directly will come. So it is coming very slow. If you need needle push into the human body, so blood will slowly coming. It's coming inside, then blood plasma is going to the sensor. So this portable system we have developed in the lab. This is all about from biosensor. For biosensing, it is used. So next will be discuss about the food. This is the last topic. I'll discuss a little bit. How much time is there, Niladri? Niladri is there. Hello.
Yes, sir.
How much time is there?
Time is left now. Near about 30 minutes is left.
30 minutes. Okay. 30 minutes left. Okay. Now we'll be going to the food. How we detect the food quality detection. In details, I'll discuss this what we have done very recently. Okay, how we can apply, because there are a lot of biases in food quality detection. We have seen in food, food is important item for the human body. Okay, if you control your food, good quality food, nitrous food, good quality of food, then most of the problem in your human body will be solved. Especially diabetes, maybe other, because you can control the protein, maybe cancer, maybe Alzheimer. So I'll tell you how he can play important role for that. Okay, so try to see the how mainly non-veg like fish and meat, how we can detect quality of, measure the quality of food, meat and fish. Here we have used the metal oxide based sensor. Okay, metal oxide sensor, whatever we have conventional metal oxide sensor use, the sensor is very low. But as I told earlier, we have mathematically model. We have make our own structure. Mathematical model we have done, design it and give better high sensitivity in comparison to conventional. So this sensor we have used in our food quality detection. Even we try to use this sensor for early detection of cancer also. Okay, this slide is not there. This is not complete. Work is not completed. Little bit idea I can give, because this is not complete. You are going to patent it. That is why I don't want to tell in details. I just little bit I can tell if I get time. Okay. How we can use for detection of protein. Protein, as I told you, proteins play very important role in human body, because it participates in different biological activities in the body. Cell division, cell mutation, okay, metabolism. It's used in many activities in human body. Okay, and I'll discuss it if I get time. Okay, so now I'll tell about the how it can monitor the food quality. We have used the tin oxide sensor. Okay, so ready-made sensor we have got. Some of the sensor it is there, capacity sensor. Mainly we have used a capacity sensor. MI structure is used. This is a COM structure. You put this type of structure, you're sensing it. You see the top part surface, sensing it very, very less. Okay, although this sensor is very, very stable, but it cannot be used in the food sense, because you require to have we have to sense a lot of gases. Okay, because spoilage of different foods or meat, fish, or other foods also, not a single gas is emitted. There are many gases, 4, 5, 6, 7 gases are emitted from there. To design of this mixture of gases is a very much challenging, I'm telling you. Okay, we have made it. We have this technology we have developed and we have made it. we have published in good journal, of course. So how we can use it? So this is a COM structure we have. So our design is different. Just tell. I skipped already. I've told this slide earlier also. I just tell you. Yeah, this structure. We have seen, we have made it a silicon structure. Then bottom layer is a covered by metallic contact with, we have used a gold here. Okay, we have gold, we have used it. It's little bit costly, but we can use this other metal also. But we have used a gold. Gold performance is better, so we have used the gold. Okay, other metal also can use it, no problem. We have tested it's working. Now, why we are using gold here? Because earlier we have seen that sensor, metal oxide sensor, they use it. It cannot work in the normal temperature. We have to increase the temperature of sensor while it is sensing, while it is doing measurement. Why? If you don't increase the temperature, then you cannot react, cannot interact with the sensing gases. So here we have done it the room temperature. If we cannot do the room temperature, we cannot go for on-site measurement, where it cannot be portable. Energy consumption will be very, very high. So that is why we have seen most of the existing metal oxide sensor. The disadvantage I've mentioned in the other side, that this sensor energy consumption is very high. Okay, you have to, our challenge is to make it less consumption, energy consumption, as well as a high sensitivity. This is a challenge we have taken up, and we have done it in our work. Okay, so how we have done, so how we do it? Okay, what we have done is we have used the gold metal, and we have doped the silver in the tin oxide. If you dope silver oxide in tin oxide, automatically band gap is going down. Band gap is going down. Okay. So if the band gap is going down, it can work in the normal temperature. It can interact properly with the other gases. I'll show you. I'll explain it. So, and for sensing, increase the sensitivity, how we have done? We increase the sensing area. So we have made the metal spots there, we increase the sensing area. If we increase the sensitivity is very, very high. There are two things we have done it to deal with these two problems. So we have used a mathematical model because spot sensor, they are not parallel plate capacitance. It is different treatment we have to use it. So there are central capacitor, fringe capacitor will be there. Since we use the patch type of metal, spot metal made it in the surface. So it is basically patch electrode. Okay, so we have used a microwave concept, patch electrode concept. So we have used a fringe capacitors for widening. We have find out the fringe capacitor, central capacitor. We have find out this mathematical model we have used for formalizing capacitor. So we have got the capacitor. This is the admittance of the function, and this is the final formula. 3.14 equation is the final formula of that. So W is the width of the thickness of the layer, different layer. Okay, W is the thickness of sensing layer. WEQ is the equivalent thickness. So that measured by the equation 3.11. Okay, and we have designed it here. We have designed it here. So we have thickness of the, how much thickness should be the sensing layer, how much thickness of the insulated silicon dioxide layer, how much thickness silicon. We have designed it. So mathematically we have designed it, and according to this design, we have got this thickness of sensor 0.8 to 1 micrometer, height of the patch electrode, the metallic electrode, spot electrode will be 400 nanometer, area of fast electrode 25 millimeters square, and thickness of solid layer is 150 micrometer. So using this design formula, we have fabricated in our laboratory. This is the fabrication step used. Okay. We have fabricated different steps. We have used it for fabricated lithography. All these things we have used it. This is the fabricated, our fabricated sensor. We have used in silicon substrate. Okay, and we have to analyze the sensor whether tin oxide deposited or not. So we have analyzed, same analysis we have done it. Whether crystal formation is there, polycrystal and nanocrystal form is there. So we have X-ray and component analysis we have done for EDX. We have perfectly got the different component in the sensing layer. Tin, silicon, carbon, we have got all these things. Same image. Now, after making the sensor, we have to calibrate it. How we have done the calibration. These are, as I told you, we have to know the theory. It is very important. So after sensing, we have seen that there is a bending on that. Due to bending, your work function is changing. You see the work function is changing. Work function is bending. Sorry, work function will be changing. Okay, work function, because the conduction and balance and all this will be changing because of the work function will be changed a little bit, and because of that, the property will be changing. And we have seen that it can work in the normal because of this bending. I'm not going to. We can read our paper. It's published in Biosensor Biosensor Journal. We can see our paper. Okay. So if you dope the silver, we have seen the oxygen content. As I told that O minus has to be developed on the surface of tin oxide Ag. If you dope it, we can increase the simple tin oxide. Whatever oxygen molecule is there, it is more in the if we made it the silver dope. Okay. If you silver dope it, automatically our sensitivity will be, because more oxygen will be captured, spill up from the body. These oxygen will be interacting with the chemical gases, not chemical, gases. Okay. This is the idea we have. As I told, that silver is dope because of that. And it will work in the room temperature. Mostly, it will work in the room temperature. So this is the absorption reaction, how it's changing. Okay, this is the reaction for different gases. Since we have tested for the fish and meat. In meat, we have seen emitted gases in ammonia, TMA, trimethylamine, dimethylamine, DMA, and H2S gas. Okay, we have seen all these gases, whatever is emitting from fish or food. So these gases will be interact with the oxygen which is made in the surface, which is temporarily made in the surface. Okay, so we have got this equation. It interacted, and because of the dielectric constant is changing, if dielectric constant is changing, your capacitance will be changing. So this is the way we have done it. Okay, this is a sensor for calibration. We have known gases. We have passed through the sensor with controlled amount. MFC used, there are 5 MFC used, and mixing the gases in the chamber, and your sensor will be there that will test it. Okay, what we have done in the, this is a mixture of gases. What we have done, separate gases we have tested, we have calibrated. Okay, then in known gases, known amount of gases we mix up in the chamber, and then we share it to the next slide. I'll show you some of the card. So we have shown how response we have got to different gases. Ammonia gas is very, very high in our sensor, and other sensors very, very low. Then TMA, DMA, we have checked TMA, DMA. Okay. So in different concentration of the gases, we have checked in different. So the ammonia is very, very high, and H2 is slightly low. Then DMA, TMA, and ethyl alcohol. Ethanol is there. The gases sometimes in fruit type of fruit, ethanol is emitted. Okay, remember, if you try to test on fruit spoilage, ethanol emitted. Calibration we have done individual gases. This is the equation, different gases we have done it. CH3, TMA, DMA, H2S, C2, H5. Because if you test the fish and food, ammonia, only ammonia cannot do. Whatever work they have done, only sense the ammonia. Okay, but we have done with the different 3-4 tests. That is our accuracy is better than others. We have got all 4 gases, whatever emitted from the air. This all 4 gases mixed together. This is individual gas, and now we have done for all the gases mixing together. We have got the results. Okay, these gases we have seen responses there, mixture of gases. So these are different gases. Other gases we have tested. So different gases also have tested. We have got this result, the experimental result. Now, how do analyze the meat? What we have done, meat image the total viable count, TBC and TBV. TBV, total volatile basic nitrogen gases. So as you know, meat having is a highly proteinous material. It's having the nitrogen gases. It's having the nitrogen gases. Okay, basic nitrogen gases. We have to analyze the nitrogen gases. Nitrogen. Okay, TBPN, if you analyze it, what we have done, we tried to, each gases we have already have done it, I have shown you, different temperature of the meat. We have taken we analyze the gases responses. Okay, so we have got this in storage time. Then we have a TBPN analysis, total volatile basic nitrogen, which is coming from the meat gases, and we have analyzed it. Okay. And we have done pH values also. These are the pH values for different gases. And analyze it. Okay. These are the different measurement, rate of spoilage at different time. We have seen that your spoilage started after and 15 degree started after 4 days. If it is in 15 degree, okay. Even if you put in the fridge also in 50 degrees centigrade temperature, so you should not take the meat or fish after day 4. Okay, it depends about 15 degree, 25 degree. We have done it. 25 degree after day 2. You should not take, even it's fish temperature. If you put the fish at 25 degrees, you should not take after 2 days, because we have seen that from standard data, we have to check the content of the gases. Okay, it is a standard data. We get it from the International Society of Food Quality Monitoring. It is a UK organization. They standardize the things. Okay, so from there we are compare it, and we have seen the fish meat after before day 4, before day 2 at temperature 50 degrees, we can keep up to 25 degrees, 50 degrees, we can keep up to 4-day for storage. Okay. So as I told you, different responses I've got it different. Now we'll go for mixing of that. Okay. We are mixing with ammonia, TMA. We have mixed it, we have got this response. So we are mixing sample 1, H2S, TMA, and H3 different proportion. As I told you. Sample 2, you have taken gases, you have taken sample 3 like that, we have got these results. We have got this. These are calibrated results. Okay, these are calibrated. We have stored in the, we have formulated, we are storing the response capacity because we have to check the capacitance of changing the gas concentration. So we have seen the capacitance at 40 degrees centigrade, we have got this different time. Okay, TBN value. Okay. 15 we have got this result. 25 we have got this result. Okay, we have taken the time up to 30 hours we have checked it. These gases we have checked it and capacitance value we have checked it. TBM is the standard value. Now we have calibrated with the standard values. Okay, standard value we have calibrated with this setup. Okay, there is a measurement, sorry, not this is a measurement setup. You put the samples inside another chamber and we have gases we put in the chamber through pump, it is coming out through valve, we have control amount of gases we can go and valve and MFC will change the concentration of gases. This is our setup in our laboratory. We have made it, picture of the setup. This is for mid-spot measurement. Calibrated measurement. Now we'll go for the different fishes we have taken, how it is calibrated, how we can test it. So 3 fishes, tilapia, iris, and rohu we have taken. We have got the capacitance at different time or different gases, similar gases. The response, corresponding response we have got in different gases. Then capacitance, we have measured it. The volatile constants we have varied and different in ppb. ppb actually your signals is coming in ppb range, not ppm range. Okay. This is the mixture of gases. Sample of 2, sample 3 we have taken. We have got TBN value and we have got TBC value. These are standard value actually. And we have find out in our by using sensor, we compare the standard value and we have detect the whether sample is spoiled or sample is not spoiled, sample is good quality or not, fish or meat quality is good or not. That we can test it. The same technique can be used for the fruit also. We have used for fish and meat. We can use it, same mix, same technology can be used in fruit also, fruit and other item, other food item. Only thing is we have to change the gases. Okay, fish, meat, nitrogen content gases coming out are emitted, but other samples like fruits, H2S will be there. Ethyl alcohol will be there, methyl alcohol will be there, fruits. Other fruits, even rice also, food in the rice also, they are also different type of gases will be coming out. There only will come the no nitrogen gas will come, nitrogen content, ethyl alcohol, methyl alcohol, these gases will come out. Formaldehyde, so these gases will be come out. Okay. We have same way we have measured it for the fish also. These are fish freshness cases. So now we can stop here. So I just again summary it. So we have in this lecture we have started from the sensor, basic of the sensor, then going to the e-sensor, e-nose, e-term, and we have discussed about the electrode, how electrode is used, electrode sensor is used for sensing the nerve signal, and ECG signal also a little bit I told. Then we have discussed about optical waveguide sensor, how it's monitored the glucose concentration, diabetic, online diabetic measurement. Then we have discussed about the food quality detection, fish, meat, and even fruit also, different food also we can do it. So, Niladri, hello. Thank you very much. Thank you very much for patience listening.
Thank you, sir.
If you have any question, you can ask me.
Thank you, sir, for nice presentation.
It is too long. It was too long because many people are getting bored actually. And actually, I have given the lecture on from my experience, whatever I have done it. Mostly, whatever I have done it, whatever we are doing here. Okay, starting from mathematical model to fabricated, then instrumentation. How we can, because sensing, making a sensor is another thing, designing a sensor is another thing, but we have to go into the equipment. Equipment is very important because then only commercially it can be used. Okay. So any question, you are welcome.
So any question you ask me, sir is ready to tell. Actually, I was the student of this great teacher.
No, not get teacher.
Actually, when we were in the student that time, whatever question we have asked in the class, also outside the class, even in night time also, he is giving the answer. So that is why I'm telling, because if you have question, you ask now also, or you can ask any time also. If he is going to by train also, he can give the answer. So
yes.
that way he's like that. He's like that. So personally, we have at the MTech level, we are very grateful with the sir. So if you have any participants have any question, you write question and answer, and also in the chat box. Please write any question.
Email also can tell. My email.
Yes.
You can write on PPS.
Yes, directly you can write. You also by email also you can talk with the sir.
If you want, we can take my mobile number also from Dr. Niladri Maity, and you can over telephone you can call me. If I'm free, then I'll surely interact with you.
Okay, sir. No question, sir. Dr. Obij, something. Please type your queries. Or yes.
One query is there.
Actually, few participant has raised their hand. That's why if they want to ask anything, they can type it in question and answer. Yes. So one question is there, sir.
Facilities for flexible electronics fabrication is there or not?
Yes. Flexibility we have started now. Even we are working on paper, the filter paper, even other flexible substrate, low cost substrate, especially for the biosensing, early detection of cancer. We are doing. We try to deposit the sensing material on the paper, and with our comb structure and spot structure. Spot structure, whatever I told, it is used for the food only. But if we use the biological stability, that's a problem because stability following that, because we cannot control the capacity. It's changing very fast. So it's difficult to measure. So we use the COM structure as I shown in the figure. COM structure, we can make it in the paper and we can fabricate it here in our laboratory. And we have got the good result because since it's not published, so I have not shown here. Okay. First in the paper, make the COM structure. Okay. By using hard marks. Then after the above that, we have put the samples. Put the samples, sensing samples. Then these sensing samples will be tested with other biological molecules, protein, blood samples. We have tested. In fact, we have got good results for that. Good results we have got. It is not published. We are going to patent, then publish it. Then only will be able to tell you. Now at present, I don't tell. It's not tell actually. This is a work of our student because it is not published. So just I am telling you, this is the way we have fabricated. And one problem in the flexible sensor is that the cycle. Okay, if you fold it in many times, then it can damage. So we have to test that one also. We have to test that one also. How reliable is that? So a lot of work is going on in foreign also. And in fact, our university, which we have our one faculty, Dr. Atul Bodwa, he has made the model for testing that design model. It is published in advanced material. So I want to take his expertise for testing for reliability of the paper sensor. Paper sensor reliability is very important. Okay, because any sensor, first thing is repeatability, reusability. These two parameters has to be there. Special repeatability. So whatever we have done this time, even after 2 hours, the same result we should get. Otherwise, it's difficult to use or difficult to commercialize. Any more questions? Hello?
Sir, one more question is asked by the same participant. Signal conditioning can be fabricated on flexible substrate.
Of course, we can do it. Signal conditioning, you can do it. There are a lot of noise will be coming out. We can use filter also. Filter the noises also. But maybe turbulence will be there when you use it. Okay. In on-site measurement, we may have a lot of problem. Okay. We may have to use in the seashore or especially the food, fish, meat quality detection. If it's flexible sensor, we have to use in seashore or some places where environment is very bad. Okay, so there is a difficult. We have to test all these things. We have to check it. Humidity, all these things, we have to check it. Okay, so there we can use the nullify these things. Then if you know the noise, known noise, we calibrate these noises, pH value. So under that condition, we have to calibrate the sensor. Then only we can avoid this problem. We have to calibration is very important. In sensing and instrumentation, we have to calibrate properly, very well. Most of the lecture I have to the calibration. In different environment, we have to do it. Okay. And we can use a filter also, conditioning, signal conditioning, we can do it, filter, we can use it. But it will not help much actually, because on spot we have to take it the signal. Okay. And noises, if it is different frequency, we can neglect this frequency domain, you can convert to frequency domain. And noise frequency, we can filter it. Okay. You can use FFT or other Fourier transform, other transform, we can use it. So signal has to be converted to frequency domain. And noise frequency, we can filter it. Then you can reconstruct the signal. And then 8. Is it okay?
I think so, sir. Another question is there. This is not the question. This is one inquiry. Can we work with your lab facility?
Yes, we can work with our facility. we can come to our laboratory for fabrication because we have this is a national facility. Only problem is that now funding is less now. We cannot provide the chemical. You purchase the chemical, we can come anytime, we can do that. You can use our facility. Only problem is that our funding is now limited. We cannot provide the chemicals. This is the problem. We can come, no problem. You can come anytime, any moment. But we have to write to us. If then we can see what are the chemical use. If it is available in the laboratory, we can reply. If it's not available, we can buy it. We can tell that, ask you to buy.
Okay, sir.